Let's see how you do this question. Question 1. The acid dissociation constant for this diprotic acid are Ka1 and K2. So this acid will dissociate once and you call this Ka1. And then after that, it will dissociate again and we call it Ka2. All right, so actually this acid has a Ka1 value, and this the conjugate base. This is a conjugate base. I say it has a Kb1 value. All right, so that's what the question is asking for. Okay, maybe just continue. This acid has a Ka2 value, and this one has a Kb2 value, the conjugate base. But the question is asking for this Kb1. So if you remember the concept, Ka1, the acid multiplied by the Kb of its conjugate base is equals to Kw. So if you want to find out the Kb for this, which is Kb1, so Kb1 equals to Kw over Ka1. All right, so that's why this answer will be C. Okay, let's look at next question. The value of pKw at 40 degrees is 13.58. All right, and then what's the pH of this barium hydroxide solution? So barium hydroxide is a strong base. It will dissociate completely to Ba2 plus 2OH minus. So you notice that they gave you the concentration of barium hydroxide, but the ratio is 1:2 when it comes to the barium hydroxide and the OH minus. So the OH minus concentration is actually 0.05 times 2. So this is actually 0.1 mole per dm cube. So there's this formula, pH plus pOH, equals to pKw. Is it okay? So you can use this formula, or you can use H plus times OH minus equals to Kw. All right. So since pKw right here, pKw is minus log Kw. Since they gave you the pKw, right? Can you see that? 13.54. So based on this, based on the formula, Kw is equals to 10 to the power minus 13.54. Right. So if you plug it in here, you can find out the H plus concentration. So H plus concentration times 0.1 equals to 10 to the power minus 13.54. Right. So you work it out. H plus, let me work it out. It's supposed to be 3.162 times 10 to the power minus 13. So trying to get pH minus log H plus concentration, we're just going to plug this in. So you should get a value of 12.54. All right, so this one, the answer is B. Okay, let's look at the next question. Question 3. In this titration, there's a phosphoric acid is reacting with sodium hydroxide. Using this information, deduce the formula of the salt form. So H3PO4, or H3PO3, sorry, will react with NaOH. So if you want to find out the ratio, the reacting, how much of each reacted, right? So this 15 times 0.1, as you can see, volume times concentration gives you the most. Here is 10 times 0.3. So if you look at it carefully, you realize that actually the ratio is 1:2. So 1 mole of the acid reacted with 2 moles of the base. So it means that since 2 moles of the base reacted, you'll pull out 2 H plus from here. So the final salt is actually Na2H, because 2H plus was kicked out. So PO3 plus 2H2O. Okay, so this is actually the salt form. All right, so the answer should be B. You see that? Okay, let's look at question 4. All right. Okay, from here, let's take a look what it means from these values. You can see that Kw is actually water to give out H plus OH minus. This Kw. So when temperature increases, okay, temperature increases, you notice Kw actually increases. So when temperature increases, it will favor the endo, because we add heat, the system will want to absorb heat. Kw increase, which means the position of equilibrium shifts right. Okay, so what this helps you to, what this does, it tells you that the reaction the dissociation of water is an endothermic reaction, because when increased temperature, it shifts right to favor endo. So this reaction is endothermic. All right. Okay, so let's take a look. The association of water molecules by hydrogen bonding increases as temperature increases. So actually, when temperature increases, in fact, it splits up into H plus and OH minus. Correct. So the hydrogen bonding increases doesn't mean anything over here. In fact, when temperature increases, I believe that when temperature increases, the molecules move further away, right? So all these hydrogen bonds will be broken. But here they say it increases, the hydrogen bonding association increases, which is actually wrong. Okay. Water is not neutral at 15. This is definitely wrong also. Okay. Because when water dissociate at a higher temperature or at a lower temperature, at any temperature, the H plus and OH minus ratio will still be 1:1. So water will definitely be still neutral at 15 or at 30 degrees Celsius. Okay, number 3. The concentration of both H plus and OH minus increase as temperature increases. Yes, because when temperature increases, position shift right. So H plus concentration increases, pH will decrease, yeah? So at the same time, OH minus concentration will also increase. So this actually statement is correct. So that's why the answer is C. And of course, this is wrong, right? We just proved that this was endothermic. Okay, let's try question 5. Okay, let's look at this next question. They showed this reaction 1, reaction 2, which of the following statement is not true. Both reactions are acid-base. Okay, if you look at the first one, CH3 looks like this. A plus, Br minus is like this. Okay, in fact, there are 4 lone pair, but I'll just show 1 lone pair. So this one is actually forming a dative bond to the carbon, right? So this is actually an electron pair donor. We call it a Lewis base. And this is actually an electron pair acceptor. We call it a Lewis acid. So it's still an acid-base reaction. So this statement is still true. In reaction 2, this acts as a Bronsted-Lowry base. So what's a Bronsted-Lowry base? A Bronsted-Lowry base is a proton acceptor. Okay, so did this accept a proton? Let's take a look. This became this. Is that so? It took in 1 H plus. So this statement is also true. Okay, so let's see. In reaction 2, this is the conjugate acid of this. So actually, if you notice, it's actually wrong because this is the conjugate base, not conjugate acid. All right. So this is an acid. It loses a H plus. It becomes this, and this is the conjugate base. This one is the conjugate base. All right. So this is false. Right. In reaction 1, the dative bond formed between. Yeah, I just told you just now. Dative bond was formed over here. So this is for part D. Okay. So the answer is in this case, or it should be C. Okay, let's look at the next question. Okay. Okay, there's conflicting interpretations of the origin of the acidity of aqueous boric acid. Okay, which of the following statements pertaining to this interpretation is incorrect? So boric acid is arsenous acid. So arsenous acid is one that dissociates to give out H plus, right, in water. So did this give out H plus in water? In water, it gave out H plus. Can you see that? So it's arsenous acid is still considered is correct. Okay. So boric acid is a Bronsted-Lowry acid. What's a Bronsted-Lowry acid? Bronsted-Lowry acid is a proton acceptor. So look at it. Did it really accept a proton from here to here? No, right? Yeah, this is 3, this is 4. No, in fact, it took in OH minus. So this is actually wrong. Okay, so this answer should be B. Okay, but let's look at the next few. Boric acid is a Lewis acid. What's a Lewis acid? Lewis acid is an electron pair acceptor, right? So did it really accept an electron pair? Let's take a look. So this is what it looks like, boric acid. So when it became this, actually the OH minus, the lone pair form a dative bond to the boron. So it's an electron pair acceptor. So that's true actually. Okay, so C is correct actually. but the question, of course, was incorrect. Boric acid is a weak monobasic acid. Weak monobasic acid because in water, it only gave out 1 H+. So yeah, this statement is still correct. Okay, so that's why the answer is B.